pleasure to be here anyways, and I would like to well, thank you all for coming, and David for the opportunity to present. So the work that I'm going to talk about today is a topic that I've been interested in the past few years or so. There is not much of the statistical mechanics here, but nevertheless, I think it's interesting. And it's work that I've been doing and I'm still doing jointly with the people whose names are on the screen. So Rodrigo Caballero, who's in Stockholm, Mike Byrne in St. Andrews, and Tim Marino, who is a PhD student in Lyon. Okay, so just to give a little bit of context, the general context of the phenomenon that I'm interested in is the possibility of abrupt changes in the circulation of the geophysical flows, which could be associated to abrupt climate changes. And the first thing that I want to say is that we know that such abrupt changes exist and have existed in the past. Perhaps the best documented evidence is the so-called Dansk-Gauge events. So what you can see on the screen right now is a time series of a paleoproxy for temperature. So that's the isotopic ratio of oxygen and based on ice cores in Greenland ice. And you can see on this recording, you can interpret it as temperature. So basically, when the value here is large, it's warmer, and when it's smaller, it's colder. So on the background, you have the glacial interglacial cycle. So this is the scale is going backwards towards the right, and the present is here. And this is our interglacial period. This is the last interglacial period. And this is basically the last glacial period. And within the last glacial period, you have some spikes in this recording, which correspond to very abrupt warmings. These warmings in the North Atlantic. There are, as you can see, they are quite strong. The amplitude of the spike is typically something like half the overall variations between an interglacial and glacial period. So locally, it's about something like between 5 and 10 degrees warming in the North Atlantic. So it's something which is significant. It's not just more fluctuations. It's also, in fact, not limited to the North Atlantic. These kind of events are global. They have a different signature in different parts of the world, but there are other paleoproxies which indicate that, in fact, at the times of these abrupt changes, something happens pretty much everywhere on the globe, including low latitudes, which we know from other paleo evidence. And these phenomena are also very fast. Here, it's difficult to say because the scale is so large. But there are some better resolved recordings which show that typically these abrupt events occur on timescales which are on the order of 10 years or maybe even less, but probably no more than that, which is quite small compared to the timescales we are dealing with here. These events are usually associated to, well, we believe they are associated to abrupt changes in the circulation of the ocean. I'm going to talk about abrupt changes of the circulation of the atmosphere. So we know we know probably a lot more about the associated changes in the ocean than the things I'm going to talk about in the atmosphere. So here I'm not going to address this problem. I just want to use this as evidence that such events exist, and that it's an interesting question to understand if there could be analogous transition in either in the ocean, which are different from the ones which are associated to this phenomenon specifically, or in the atmosphere, and which maybe we don't know about yet, and which could play an important role either in climates in the future, or potentially in all other climates of the past. So that's the main motivation for the question which I've written here. Okay, but I'm going to leave that here for the rest of the talk, and no longer talk about Dansk-Gauge events. Yes. So it's the other way around. The increase here is very fast, and then it decreases more slowly. It's just because the time scale is reversed to perhaps what you're used to, but paleoclimate people prefer it like that. Yeah. But it's definitely not symmetric. So it has a specific sawtooth shape. Yeah. Okay. So it's also the question of multiple equilibria and abrupt transition it's a question which, from a theoretical point of view, is interesting. So let me first make a bit more specific what I mean by abrupt transitions. So what I mean is probably not very surprising for many of you. I'm not so much interested in transitions which are abrupt in the sense that the slope on a curve like this, so the response of the system when I vary some control parameter is large. This is not so much what I'm interested in. I'm more interested in cases where you actually have a bifurcation because it changes the dynamics quite a bit, in the sense that if you have bifurcations, like back-to-back saddle node bifurcations, well, then it means that your phenomenon is not reversible. So if you go across this bifurcation, you have to go all the way back to the other bifurcation to go back to your initial state. So that's a hysteresis phenomenon. That's the kind of behavior that I will be looking for in the atmosphere here. It changes also what happens even when you don't reach the bifurcation here. Because if you are living here in the bistable regime, and your system fluctuates like most systems do, for instance, if it's a turbulent flow, the spontaneous fluctuations of the system might generate a transition across the potential barrier here, and then you end up in the other state with perhaps some statistical properties that you would like to be able to quantify. So this is the kind of situations that I am interested in. And it happens that we know that such situations occur in a variety of turbulent flows. So in fact, it's not surprising. It would not be surprising at all if large-scale geophysical flows also exhibited this kind of behavior. So here I've listed a few examples of such behaviors. The first one is from an experiment in Saclay. It's called the von Karman experiment, or also known as the French washing machine. It's basically a cylinder of fluid, water in this case, and with impellers on the bottom and top plate, and you can control the relative velocity of these two plates. It generates a very strong turbulent flow. You can control, for instance, the torque applied on each of the plates. And as you do that and you vary the torque, you observe an hysteresis phenomenon. If you are in the regime where several equilibrium states are supposed to exist, and you just let the system evolve, you observe spontaneous transitions like this between one large-scale circulation and another in the cylinder. So it's exactly the kind of phenomenology I was talking about. A similar behavior exists also in the von Karman sodium experiment, which is more or less the same, but filled with sodium instead of water. And this generates a magnetic field which has random reversals. So it's another example of such a phenomenology. Perhaps closer to the atmosphere, there is a famous experiment which was carried out in the group of Harry Sweeney at the end of the 90s of a rotating annulus, which exhibits transitions between a zonal flow and a blocked flow, which was taken as an analog of the transitions between zonal and blocked regimes in the atmosphere, which are important for the mid-latitude dynamics and the weather. And I could go on. There are many other examples of bistability and spontaneous transitions in turbulent flows. I have also another example coming from numerical simulations this time. Numerical simulation of the barotropic vorticity equations, which is a very simple equation, probably the simplest system you can think of, which generates zonal jets. And the number of jets in this experiment varies. So for instance, here you have, this is a Hofmüller diagram of the vorticity. You see that in some cases you have 2 jets, and sometimes you have bifurcations, you can see 3 jets, and so on, the number changes. So again, this is just a small selection of examples, so I apologize if your favorite example is not in the list. But it suggests that this is in fact probably a very generic behavior with turbulent flows, and it's something we could expect very naturally. So now I will go back to the circulation of the atmosphere, and I want to focus on one possible candidate where it's reasonable to expect that we could have bistability and spontaneous transition, and that's the example that I will be discussing during the rest of the talk. And it's a phenomenon which actually occurs in the tropics, and it's called superrotation, or sometimes equatorial superrotation. So let me first define what I mean by superrotation. So a planetary atmosphere is said to be in superrotation if angular momentum is somewhere in the fluid larger than solid body rotation at the equator. So in other words, if you take a ring of fluid at the equator, initially at rest, and you move it poleward, so it conserves its angular momentum, and it corresponds to, so it acquires zonal velocity to conserve the angular momentum. So it corresponds to the curve, the dash curve here. Okay. So if anywhere in the atmosphere you are above this curve, it means that you are superrotation. The black profile here, the solid curve with an N for normal because we live on Earth, is a sketch of the profile of the zonal winds on Earth. And you see that it never crosses this angular momentum conservation profile. So it's not superrotating, at least on average. And you can recognize the mid-latitude jets on this profile and see that in the tropics, the wind is actually on average easterly and weak, and it's always below this curve. So you could imagine a hypothetical planet where in fact the curve crosses this line, and here you have superrotation. The angular momentum is larger than solid body rotation at the equator. It's not actually so hypothetical as a phenomenon. It happens on a number of planets. For instance, in the solar system, it happens on Saturn, Jupiter, Venus, or Titan. So there are actually many examples around us, and also some examples a bit farther from us. Exoplanets, or some exoplanets, at least a large class of exoplanets, called Jupiters, are believed to be in superrotation. For some of them, astrophysicists actually claim to have observed evidence of superrotation. I think it's the case at least for this one. So I don't know if it has a more poetic name than HD 189733b. And maybe this one as well, but I don't remember for sure. So there are examples of actual superrotation in nature. Okay. So now the question that I want to address in the talk are, can there be abrupt transitions to superrotation, or bistable regimes where you could have at the same time a superrotating state and a conventional, so non-superrotating state? If so, what are the parameters which controls the existence of these transitions? And are they relevant for the climate of the Earth? Is it something which is possible? And if it's possible, does it really affect the climate of the Earth or not? Okay. So the last one I will only briefly touch upon. Okay, so that's basically what I want to talk about. So to do so, I will start by a short summary of some of the important dynamical mechanisms to generate superrotation. I will not go too much into the details. I know that Jeff Vallis has given a talk on this topic here recently, and he did it. I'm sure I wasn't here, but I'm sure I did it much better than I could possibly do. So I will just focus on the small part that I will need for the rest of the talk. And then I will go on to discuss the actual feedback mechanisms which can be responsible for bistability and abrupt transitions. Okay, so here is the zonal momentum or zonal acceleration balance. Written in spherical coordinates, and it's zonally average, so average around a circle of latitude. So it's decomposed into different terms. You have the Coriolis acceleration here, the effect of the mean meridional circulation, so the bar here is a zonal average, and the eddy fluxes, which I've written as F here, plus some dissipation terms. And we want to understand how to generate a jet in the tropics. So there are some terms we know cannot achieve this. The mean meridional circulation cannot create a maximum of angular momentum if there is not already one in the initial condition, because it conserves angular momentum. So it has to be some other terms. It cannot be the dissipative term, because we expect dissipation to transport angular momentum down gradient, so to mix it. So it has to be the last one, the eddy fluxes. So we need some eddies to transfer angular momentum up gradient. So I guess that's why this topic fits into the general program that we're here for. But still, there are many ways that you could do that. generate these anti-diffusive momentum fluxes. There is one general framework which is very widespread in geophysical fluid dynamics because it governs, it plays a crucial part for the dynamics of the mid-latitude jets, which is that as soon as you have Rossby waves generated from some source, you have acceleration toward the east of the jet at this location. So that's the standard argument. So if you have a jet like this, you generate Rossby waves, which propagate away, and they transport momentum and energy in different directions. So they propagate, if you have a wave packet here, the velocity is northward in this case. The momentum flux should be southward and the opposite south of the jet itself. So this is a standard mechanism to generate an eastward jet in the atmosphere. So it would be natural to think that something like that would apply also in the tropics. But it's indeed we're going to need some source of eddies and waves, but it's a bit more complicated maybe in the tropics and at the equator because we don't have geostrophy basically. So the waves and eddies which are going to play this momentum transport role are a bit different. So there are several routes to superrotation which are known to generate this momentum transport towards the equator. The first family of mechanisms you can think of are mechanisms where the setup is completely axis symmetric. So you impose you don't break the zonal symmetry. But the system generates eddies itself through some hydrodynamic instabilities. So, for instance, there is a series of papers by Mitchell and Vallis where they show that you have a transition to superrotation. So the blue lines here are the contours of zonal wind. So here you have something which looks more or less like the Earth. And as you change some control parameter, which is called the thermal Rossby number, you have a transition toward the superrotating state. For large thermal Rossby numbers. So this scenario is thought to be associated to an hydrodynamic instability called the Kelvin-Rossby instability, which involves the coupling of the Kelvin wave at the equator and a mid-latitude Rossby wave. There are other variants of this, but the main characteristic is that the eddies are generated by hydrodynamic instability. You can also force the eddies directly. For instance, something which is more similar to what people do in turbulence, 2D turbulence or quasi-2D turbulence, is to have some vorticity forcing, usually small scale random vorticity forcing. So this has been done as well, in particular using the shallow water equations. And if you force vorticity in the tropics, you will also generate some eddies transporting angular momentum towards the equator and see the formation of a jet at the equator. So this picture is from Scott and Paul Vanni, but there are a number of papers who explored this kind of possibilities. Instead of forcing directly vorticity, you can impose some heating in the system. Here the reasoning is that the heating could stand for different physical mechanisms, like, for instance, convection. We'll talk about that later. Or potentially the day-night contrast on an exoplanet. For instance, if you think about a tidally locked exoplanet, you have a very strong zonal gradient in the heating. Okay, so here I'm showing an example of a paper where it was indeed imposing a large-scale eddy heating and generated a transition from a state which looks more or less like current Earth to a superrotating jet at the equator here. And finally, there is a family of other studies where the eddies are not, well, the route to force the eddy is not so clear, in the sense that some other parameters is varied. The forcing in the simulation is different, but it turns out to affect the circulation in a way which transfers momentum towards the equator. So for instance, an example of that is the simulations which were carried out by Rodrigo Caballero and Matt Faber, in which they simply increased the CO2 concentration in an atmospheric GCM, and they observe a spontaneous transition to superrotation. They need to go to very high values of CO2, 30 times the present pre-industrial concentration. The motivation was that they were interested in some very old climates, the climate of the Eocene, roughly 50 million years ago, which are known to have much higher CO2 concentrations than today, but maybe not that high. But nevertheless, what is interesting is that they don't do anything else, and still the system generates a transition to superrotation. And there are other similar studies. So here I will focus on just one of these routes to superrotation, the third one, where we have some non-zonally symmetric heating term. And I will discuss how this scenario is compatible with the possibility of having an abrupt transition with hysteresis. It's actually something which has been suggested early on, as early as in the 90s, with relatively simple models, where people noticed that imposing this kind of forcing tended to generate a very abrupt transition to superrotation. Okay, so let me go back to what the non-zonally symmetric forcing we impose in this kind of scenario stands for. So here I'm showing a picture. So like I said, it could also be interpreted as a day-night contrast on exoplanets. Here we'll focus on the interpretation which is more relevant to the Earth, so interpretation in terms of convection. So what you can see on this picture is the heating rate directly measured by a satellite, more or less at mid-level in the atmosphere. So it's in Kelvin per day. And it's average over a long time. So you can take it as a sort of stationary heating. And you can see that it's not homogeneous. There are some regions which receive much more heating from convection than others. In particular, the regions over the maritime continent, where convection is strongest, or also over the rainforest in South America. So there is some special structure to this forcing. It's not zonally invariant. There are other ways in which latent heating in the tropical atmosphere is non-zonally invariant, which are a bit more complex. In particular, it's not necessarily stationary. One important way is the so-called Madden-Julian oscillation, in which you have structured convection, which organizes into a cluster of convecting towers, and which propagates. So basically from the Indian Ocean towards the Pacific Ocean. So here these are pictures made by averaging some events, some independent events of Madden-Julian oscillation at different phases of the oscillation. And you can see the propagation of the anomaly. Here it's an anomaly of precipitation, but you can interpret that as an anomaly of heating, which propagates toward the Pacific. So in reality, there is some complex structure. There is part of this heating which propagates. There is part of it which is stationary. Here, I'm not going to consider all these details. I just want to use it to say that there is some non-zonally symmetric heating, and which I will represent in an idealized way in the theoretical work and also the numerical simulation that I will show later. So let me explain first the theory. Why do we expect this scenario to lead to superrotation? So I will do so by using the simplest model that I could think of, which is the shallow water equations on an equatorial beta plane, and they are linearized around a state of rest. So this is a very simple system of equations written here, describing zonal and meridional momentum and the height of the layer of fluid, or I will probably call it geopotential later in the talk. So the dynamics is in blue here. I encoded it in a more formal form here as the linear operator L. And on the right-hand side, you have forcing and dissipative terms. The dissipative terms are in green. Here we just have some linear friction acting on velocity and some radiative cooling, which I also take to be linear for simplicity here, with some specific, some relaxation time, if you want, for radiation. which is also encoded in a different matrix D. And there is some heating term, which I write in red here in this vector. Now, this system has been studied for a while. We know very well, for instance, that it supports waves, well-known equatorial waves, which are just the free modes of the equation I've written here. They are the eigenmodes of the operator L. So we can plot, for instance, the frequency omega as a function of the zonal wave number k, and we recover a famous picture which shows the spectrum of the operator with the Rossby waves here, which are the low frequency components with solid lines here, the inertia gravity waves here, propagating eastward or westward, the Yanai wave, which makes a connection between the two, which behaves as a mixture of both Rossby and inertial gravity waves, and the Kelvin wave, which is the non-dispersive wave here. So this has been known for a long time, since the work of Matsuno in the 60s. I'll show you just briefly how two of these waves look like. It's supposed to play automatically. So that's a Kelvin wave. So it propagates toward the east quite fast. It has a geopotential anomaly, which is centered at the equator, and zonal wind, and wind which is purely zonal, a wind anomaly which is purely zonal. Now the Rossby wave, I'm taking the one with meridional wave number 1. It propagates toward the west, and it's much slower than the Kelvin wave, and it has some lobes on both sides of the equator with a wind anomaly, which is more or less in geostrophic balance with this geopotential pattern. So these two waves are going to play an important part in what comes next. So now I've talked about the free modes. What happens now when we consider the effect of the forcing? Well, it's again relatively easy. It's just a linear system. So we can compute the response to any forcing, because we just have to invert the linear equation. The interesting part is that, so we can, for instance, decompose it on the eigenmodes of the operator L. The interesting part is that this response is going to be very important for the transport properties, which we'll be able to compute from this linear approximation. So here I'm showing in this panel the forcing as white lines. So it's a harmonic forcing with wave number 1. And the stationary response is in color. So the geopotential pattern is the red and blue colors here. And you can see that in this case, the forcing projects on the two modes, a Rossby wave corresponding to the lobes here, and a Kelvin mode corresponding to the bulge here. So it's a combination of the two. That's the main contribution to the response. Okay. So what we can do, yeah, go ahead.
We set 2 equal 12, or 1 over 2 equal 12 in your last expression.
Absolutely, absolutely. Here I've made this choice just to be able to write this expression. Otherwise, you can still invert this linear operator, but you don't have such a simple expression. The main reason for that is that later it will be useful to understand the resonance mechanism, which it's easier to understand it if tau is 1 over alpha. But
an assumption for the rest.
So it's actually, I will relax this assumption later. Here it's just for simplicity. But it's actually a good point. It's important. It can be important in some cases. So here I'm showing that, in fact, the actual anomaly of geopotential and wind on Earth is not so different from such a simple computation. Here on the background, you can see it's precipitation, but it's more or less the same as the heating rates I was showing in the previous slide. And the solid lines correspond to the geopotential anomaly, and the arrows correspond to the wind anomaly. And you can see that, in fact, the circulation generated by this by the heating associated to convection is not has some resemblance to this very simple computation. So it's not completely oversimplistic to compute this kind of a linear response. So now, like I said, we can compute explicitly the Reynolds stress associated to this linear response. Again, it's very easy. And we see that in this case, it has this shape as a function of latitude here, and it's positive in the tropics at the equator. which shows that the waves generated by heating indeed transport momentum towards the equator. And therefore, they could force the act to accelerate the flow towards the east, as you can see in the equation for the zonally average zonal flow. So this kind of reasoning is based on quasi-linear approximation. So it means that you assume that you have a separation of scales between the eddies, which are fast, and the evolution of the mean flow, which is much slower. Okay. In fact, there is a subtlety in this model in the shallow water equations, which is that this acceleration is compensated by this term, but in fact, it doesn't apply for the multi-level case, so we'll not comment on it. Okay. So actually, in a stratified atmosphere, we can do the same thing. We can impose some non-zonal forcing, a heating term, and see if it generates the same kind of eddy response and if it leads to superrotation. So here I'm showing numerical experiments with a model solving the primitive equation. So it's a dry model of the atmosphere. There is no water vapor. So it solves the primitive equation, 3D primitive equation, so it's hydrostatic. Otherwise, it's a fairly standard dynamical core. And it's used in a configuration which is very simple in the sense that there is no, the only representation of other physical mechanisms beyond the dynamics is just through a friction, a linear friction in the atmospheric boundary layer at the bottom of the domain, so that's the F term here, and some heating term here, which is a Newtonian relaxation to some prescribed temperature field, and which stands for the effect of radiation in a very simplified way. So this is a standard setup known as a Hadley setup, which has been used a lot for ideal studies and comparing dynamical cores. So if we do that and only that, and we pick some, we are free to control the meridional temperature gradient of the radiative equilibrium state and the vertical temperature gradient. So if we pick some values, we have a circulation which contains the main features of the observed circulation. So that's the panel on the right. On the left, you have the temperature structure, which again, well, is a reasonable stratification for the atmosphere. So on the right, you recognize the mid-latitude jets here in colors, and the contours indicate the mass stream function. So you recognize the Hadley cells and the Ferrel cells here. Okay. So that's the base state. And now I want to add some non-zonally symmetric heating term corresponding to the effect of some enhanced convection, for instance. So here I choose something which is harmonic. It could be propagating or not, confined in the tropics. So I choose the size delta phi here of the region where the forcing applies, and which projects on the first baroclinic mode, more or less. It's again a choice which has been made in a number of other papers before. So it's an idealized forcing, but which has the merit of being simple. So here, before applying this forcing on top of my Hadley forcing, which generates the mid-latitude jets, I will apply it alone. So I will use my GCM to solve the primitive equation. So I have a stratified atmosphere, and I will look at the Matsuno-Gill problem. So just the linear, so sorry, not the linear, the response of the atmosphere to this forcing, but only this forcing. So it's really the analogous experiment to the shallow water computation that I did before. So if we do that, you can see the same kind of plot as I did for the shallow water equations. You have the contour lines showing the forcing. So the heating amplitude here. Here I've chosen wave number k equals 2, but it doesn't matter at all. And the colors correspond to the eddy geopotential generated by the heating, and it's very similar to the response in the shallow water model in the sense that it contains again a Rossby component and a Kelvin component, which is perhaps not as clear from where you are as in the shallow water model, but which is here. And it behaves in a way which is quite linear. If I change the amplitude of the forcing, the amplitude of the response is proportional and so on. So linear response applies well in this system. And as you can see on the right, if you compute the eddy momentum flux convergence, you see that as soon as the eddies here become strong enough, they start converging angular momentum at the equator, which means that they are pushing for the formation of an equatorial jet. Now, if we look at the same thing, but this time with a different background state, which has mid-latitude jets, because we have a meridional temperature gradient now, the response is no longer so clearly related to the one in the shallow water equations. It's still relatively close to linear in the sense that we are forcing mostly k equal 2 modes. It still has a component on the Rossby mode, a component on the Kelvin mode, but it's a bit more complex. As you can see here, the structure is a bit more complex. There is a bit of nonlinearity, and there's not a one-to-one mapping with what we saw in the shallow water equations. Nevertheless, these eddies still converge angular momentum at the equator, and you can see some positive acceleration appearing here at the equator if you force strong enough. Okay. And indeed, if you force strong enough, you observe the formation of, you observe westerlies appearing at the equator. So first of all, they're relatively weak. And when you keep increasing the forcing, they become much stronger, and you get your super rotating state. Okay. Here I have some animations to show what it looks like. For 3 different values of the forcing, this is the conventional state, which is not super rotating, and the other 2 are weakly and strongly super rotating. So you can see that so it's relatively low resolution. It's all T42, so it's not super turbulent, but there are some fluctuations. It's not too sluggish. Okay, so that's basically the scenario corresponding to the formation of super rotation when we are imposing some non-zonal heating, for instance, strong convection in an idealized way. Now, what I want to do is to explain how this can actually lead to bistability. So I go back to the theory that I presented in the shallow water equations. This is the same slide as before, and I will add a component in the equations. I will add the effect of a background wind. So now there is some non-zero background state, which is purely zonal, and this has the effect of Doppler shifting all the modes here. So that's where it's useful, in the sense that it changes the amplitude of the response for the different modes. As you can see, depending on the value of U bar here, the amplitude of the decomposition of the response on all the eigenmodes of the system is shifted. So again, it's just a standard linear oscillator, forced oscillator, but it's quite clear here. So the idea is that if you vary this background velocity, when you get close to one of the eigenfrequencies of the system, you're going to have a resonance. And if this resonance is associated to some positive angular momentum transport or just a zonal momentum transport, you might expect that this gives you a positive feedback. So here on the bottom left panel, I have computed the Reynolds stress as a function not only of latitude as on the right hand panel, but also as a function of this background wind U bar. So the right panel here is just a cross section for U bar equals 0. And now I can, for instance, look at the Reynolds stress at the equator as a function of U bar, because that's the cross section in the other direction. So it's the blue curve that you get on the right. And you see that indeed it has 2 resonance peaks, one corresponding to the phase speed of Rossby waves, and one corresponding to the phase speed of Kelvin waves. So here you see that you have a positive feedback in the sense that the acceleration of the jet gets stronger when the jet itself gets stronger. So if the jet gets stronger, it's accelerated more toward the east, it gets stronger, the acceleration gets stronger, and so on. So this is typically what is meant by positive feedback. Now, this blue curve is not the only acceleration term in the zonal momentum balance. So to reach a steady state, it has to be balanced by something else, which we can think of for simplicity as a linear friction represented by the orange line here. And we see that in this model, we have multiple equilibrium states as soon as the orange line intersects multiple times the blue line, which is the case in the picture that I made. And the interesting feature is that it gives you a graphical understanding of what a criterion for bistability could be. The criterion is that if the resonance here is narrow enough, you expect bistability. If it's wide, if we broaden it a lot, then we don't expect bistability because it will look like this. Okay. In fact, you can write that very simply as a combination of well, you have a control parameter which tells you if you expect bistability or not, based on the zonal wave number of the heating, the phase speed of Rossby waves, and the friction parameter alpha. So again, here I'm assuming that it's the linear friction has the same time scale as the radiative cooling. Okay. So to test this picture, I go back to the idealized GCM. I make hysteresis experiments. So I vary very slowly the heating amplitude, Q0, until some large value, a value at which I know that there is superrotation. And then we go back slowly again and see if there is hysteresis or not. In this case, as you can see, for different values of the zonal wave number, there is no hysteresis. It's actually a smooth transition to a superrotating state, which is illustrated on the right for Q equal 2, which has also a reduced Hadley circulation. So it's quite a different circulation from the starting point, but the transition is not abrupt, it is actually continuous. So this is in contradiction with the theoretical argument given before. So an hypothesis, possible explanation for that is that there is on top of this resonant acceleration a mechanism which counteracts it, which is a negative feedback. And a good candidate for such a negative feedback is the absorption of extratropical waves at the equator or in the tropics. So waves generated by the baroclinic instability, which propagates toward the equator and which are absorbed at critical latitudes and damp the mean flow. So to check this hypothesis, I ran hysteresis experiments suppressing artificially the baroclinic instability by setting the meridional temperature gradient to 0. You don't have any mid-latitude jets anymore when you do that. And then you recover bistability, and so you have this, the hysteresis experiment leads to an hysteresis curve. The superrotating state is different. Now it has a strong jet at the equator, but nothing in the mid-latitudes. It has also a reversed Hadley cell, which is a bit surprising, a bit unusual, but why not? And something which I'm not showing in detail is that this case is very well controlled, is very well described by the quasi-linear wave-jet theory that I presented for the shallow water equations. In fact, it is quasi-linear if you do, if you conduct the same simulations, but shutting down the AD-AD interaction, you have almost the same curve. Okay, so if you switch off the baroclinic instability, the simple wave-jet theory describes very well what's going on. It corresponds to a resonance between the waves and the equatorial jet. Now, if we go back to the case where we have baroclinic instability, we can still have bistability in some cases. So the experiments here correspond to the case where we increase the friction time, or in other words, decrease the friction coefficient alpha. So it's a less dissipative system, and you can have the intuition that this is more likely to lead to bistability because of this criterion. Alpha is at the denominator, so if I make alpha smaller, my criterion is better satisfied. And indeed, for most of the wave numbers that I've used as a forcing here, I indeed recover some bistability range and hysteresis phenomenon. In fact, the explanation for that is a bit more subtle than what I just said before, because you have two effects when you change the friction parameter. The first effect is that you make the equatorial wave resonance indeed stronger. So you make the resonance peak narrower, which leads to a stronger positive feedback due to the purely equatorial part of the dynamics. But you have another effect, which is illustrated very well in this picture. So that's the zonally average zonal wind in the non-superrotating and superrotating state. So for the same value of the tropical heating Q0, so they coexist. You could imagine that you could have transitions between the two, which is that, as you can see on this picture, the jet here is not so similar to the jet in the control run. It has moved toward the poles, and it's also more barotropic. This is something which was already well known, but in our case, the consequence is that it leads to a weaker negative feedback due to absorption of Rossby waves at critical latitudes in the tropics, both because the baroclinic instability itself is weaker, and also because the jet at the equator is more isolated from what happens in the higher latitudes. So the critical latitudes are farther away. Okay, so here I try to sum up what I've said in this part. So this is a diagram showing for different values of the meridional temperature gradient and different values of the heating when you have bistability or not. That's the blue region. So if you want, the blue lines here correspond to the position of saddle node bifurcations as a function of the parameters. Something which I've not described is that when these two saddle node bifurcations collide, you have an interesting phenomenon where self-sustained oscillations appear between a weak and a strong superrotating state. When you decrease friction, this whole structure here moves to the right, and the bistable regime exists even for larger meridional temperature gradients. So here I've summed it up for a range of values for the friction time, and shown that there is a range of regimes where the system is bistable, and another part of the diagram where it's monostable. So bistable means we are on the left of this point. There is a value of Q0 for which the system is bistable, and which summarizes the main finding of this part of the work, which is that the existence of bistability is governed by a competition between two effects: the positive feedback, which is the equatorial wave jet resonance, and the negative feedback, which is the absorption of extratropical waves. Okay. So I intended to skip this part even initially. I think I should stick to my initial plan, and right, because I want to have a few minutes to talk about the last part.
Yeah, well, you've got to have use the.
Okay, so I will do what I intended initially. Then there's a second. I will just say a few words. There is a second positive mechanism which has been suggested by Isaac Held, which is related to the vertical advection in the Hadley cell, and which could potentially lead also to a bifurcation and abrupt transition to superrotation. But basically, the problem with this, it exists. So we saw this. So in the original paper, they constructed a theory for this Hadley cell feedback mechanism and showed that it existed in a 1D model. We checked that it was still visible in a 2D model, which solves actually the primitive equation, the axisymmetric primitive equations on a continuously stratified atmosphere. So the mechanism is still there, but it's very sensitive to small changes in the vertical discretization and the vertical diffusion, which means you can kill it quite easily. So for this reason, I will not talk about it now. Instead, I want to take a few minutes to discuss the potential relevance or potential impact of superrotation for climate. So at least the coupling with other parts of the the atmosphere, which are very important for climate. So here I'm going to show the result of simulations where superrotation is not generated spontaneously, but where we really impose it by imposing some eddy forcing. So we put a torque on the system. Basically, we just have some eddy forcing, which is imposed in the right-hand side of the momentum equation. So we make sure that the atmosphere is superrotating. It's a bit of a violent way, but it's an easy one. But on the other hand, what we do is we take a configuration of the model which is much more realistic in the sense that it includes many of the aspects which were all lumped together into this Newtonian relaxation in the previous simulation that I showed. So here we are using the GCM in a configuration where it's no longer dry, it has moisture, and you can have phase changes, so latent heating and so on. Still, there are no clouds. We could have done it, but at the time it was not in the model. There's a slab ocean, so it just acts as a thermal inertia. The radiative transfer is solved with a full radiative code, so it's no longer a prescribed radiative equilibrium. We still assume that it's permanent equinox conditions, so there is no seasonal cycle in the simulations. So there are balance between idealization and realism. And there are also all the usual parameterizations for convection, vertical transfer in the atmospheric boundary layer, and so on. Okay. So in this, and I didn't say it, but it's aquaplanet, so all the surface is ocean everywhere. So in this setup, the control line looks like this. So again, you have some mid-latitude jets. They don't have exactly the same structure as in the previous ones, but the forcing is different. And if you increase the amplitude of the imposed forcing, as expected, we are generating superrotation. So it's a two-stage process. First, we are generating relatively weak superrotation here. And if we keep imposing a larger torque on the atmosphere, we get a much stronger jet, which is really focused, concentrated at the equator. And what we want to do is see how the other fields, for instance, moisture, but also surface temperature and precipitation, which I will show in a few seconds, change as we move to the superrotating state. So here I'm showing surface temperature on the left, precipitation on the right, for the control run, so non-superrotating in blue, and the superrotating state in orange. And there are actually some very strong effects, and because in this, again, we are the only thing we are doing is forcing the momentum equation. We are not forcing the temperature equation in any way. Even we're not changing the composition of the atmosphere or anything. Nevertheless, there is a large warming at the surface, especially in the mid-latitude. Globally average, it's a 3-degree warming, so that's roughly the same effect as if you double CO2. So it's quite large. And in the mid-latitude, it's much more than that. It's on the order of 10 degrees or close to 10 degrees. So there is a very large effect on surface temperatures, actually, of the transition to superrotation. And there is also a strong effect on precipitation. You can see that the precipitation distribution is much flatter. Instead of a large peak at the equator corresponding to the ITCZ, we now have two sub-peaks, which we could call a double ITCZ. The subtropics are also much moister in a superrotating state. So you can imagine that a precipitation distribution which changes like this could affect significantly things like vegetation, for instance. So to try to understand a bit better these changes that we observed and relate them to the circulation changes. So first of all, for precipitation, it's actually the main reason is that the Hadley cell, the meridional circulation, is strongly weakened in the superrotating state. So you kind of expect that it will change very significantly the distribution of precipitation in the tropics. We change completely the parameters of the convective zone where you get most of the precipitation. So that's quite natural. For surface temperature, it's much more surprising. So what we did was to try to interpret that in terms of changes of the top of the atmosphere radiative budget. So the radiative budget, I will call it R here. So that's the difference between the incoming solar radiation and outgoing long-wave radiation at the top of the atmosphere. And delta R is the change of the radiative budget between the control run and the superrotating state. Okay, so and the thing I will do is I will decompose this quantity into two terms. So it's a methodology which is quite classical, but I don't know if all of you are familiar with it, so I will explain the basics. The idea is to decompose the changes of top of atmosphere radiative balance changes into what we call the forcing and the feedback. So the forcing F corresponds to the immediate effect, the very fast processes, which are directly related to changes in the circulation. And the feedbacks are proportional to the changes in surface temperature, which we expect to be much slower. So it's kind of a decomposition into what is really directly the consequence of the forcing that we impose in the dynamics, and the effects which require some adjustment of the surface. And we further decompose the forcing into components due to changes in temperature and changes in humidity, and the same for the feedbacks. There is the Planck feedback, which is a uniform change of temperature across the column. The temperature feedback, which corresponds to changes in the lapse rate, so the vertical structure of temperature, and the humidity feedback, which corresponds to changes of the humidity distribution on the column. Here I use relative humidity, so it's not what used to be standard, but I guess it's here it's very important, but it's maybe a technical detail. And the idea is that we can actually compute all these terms because we have access to a quantity which tells us what happens for the radiative budget if we change temperature or humidity locally in the atmosphere, and that's called the radiative kernel. Okay, so it's one of the ways people compute the climate feedback parameters. So here we are using such a kernel, and we make the assumption that all the changes are small so that we can use just some linear expansions to compute all the parameters based on this radiative kernel, which is the partial derivatives of the radiative budget with respect to all the variables. Okay, so this is computed offline. It's not in the runs that I showed before. And it's been done by someone else before. So these are the results. I'm sorry, the figure is a bit small. The top panel corresponds to the changes in the top of the atmosphere radiative budget. And each of these curves here is the sum of the two color curves in the middle and bottom panel. The middle panel corresponds to the forcing terms, F. So you have Ft, which is the green curve, H for humidity, which is the red curve, and the same thing for the feedbacks here. And what this decomposition allows us to do is to understand that the tropics and the mid-latitudes actually behave in very different ways. In the tropics, as you can see here, let's say from 30 south to 30 north, the changes in the radiative budget are entirely explained by the forcing, which means that they can be attributed to the direct effect of the changes of circulation. In particular, the fact that the Hadley cell basically collapses, which changes completely the transport of the energy by the circulation. So basically, you have an increase of energy transport, meridional energy transport by the circulation at the equator, and a decrease in the subtropics. So it explains the sign of these two parts. It's negative here and positive here, because this change of transport has to be compensated by a change of outgoing long-wave radiation. Okay, and in the mid-latitudes, things are much more complicated in the sense that the forcing component basically vanishes. So all the changes that we observe are associated to the feedbacks related to the changes in surface temperature. So again, there is a connection with the fact that the energy transport changes significantly in the superrotating state, but the ways in which the system adjusts to these changes are more subtle, and they are related to the adjustments, slow adjustments of the surface temperature, which is not the case in the tropics. Okay, so I think that's all that I will say about that. And I will just summarize the main conclusions, the things that I have presented today. So the first one is that there are two positive feedbacks in the tropical atmosphere. There is only one which I already talked about, which is the wave jet, what I call the wave jet feedback, based on a wave resonance. The other one is the Hadley cell feedback that I didn't really mention. This positive feedback compete with negative feedbacks like the absorption of extratropical waves to determine whether or not we have an abrupt or a continuous transition. So in our idealized simulation, we have identified the parameters which control this competition and the outcome which results. And finally, I briefly showed that superrotation might actually have some important consequences for climate because it affects the water cycle and surface temperature through radiative feedbacks. So in reality, the two should be coupled. Here we have imposed superrotation in quite a brutal way, but nevertheless, I think it's an interesting effect which was not known up to now. So I will stop with some prospects related to a better understanding how these results apply to the actual atmosphere. First of all, by understanding whether the bistability regime is relevant or not for the atmosphere of the Earth, which requires going from the very idealized processes in the H2RS framework to the actual atmosphere. And also understanding whether the phenomena and mechanisms we have observed in our aquaplanet simulations also are robust to while going to a more realistic model. Thank you very much. So everything that I've shown here, the hysteresis experiments and so on, I've always showed the mean wind at the equator. So if I understand well, your question is whether the size of this region would matter or spatial effects would matter, right? Yeah. Yeah. Mm-hmm. So it's I think it's an interesting question, especially since we know that in spatially extended systems, the bifurcations don't necessarily play out in the same way as in low-dimensional systems. So here, in the runs that I've seen, there is not a lot of variations in the, for instance, the spatial extent of the superrotating region. Either you have superrotation and you have a jet which has a more or less the same size all the time. But what could be interesting, and which I have not done, is to focus on transients and see how the equatorial jet forms. Does it nucleate around some fluctuation locally and then extends spatially both in the longitude and latitude direction? That I don't know. It's a good idea. Yeah. I wouldn't be able to say from the simulations I have, because you would have to have a much higher frequency output to be able to actually see that. But it would be easy to do, actually. Yes. Yes, absolutely. I agree. Yep.
in the case of low friction, these different mechanisms would balance each other without necessitating friction.
So in my experiments, friction played a dual role. First of all, it controls the properties of the resonance, and it also affects the negative feedback by changing the base state, in fact, not by acting on the feedback itself. I think what would happen in a more realistic setup is that this would be controlled by turbulent transfers, vertical transfers of momentum. I would still expect that they affect the properties of the resonance. For the other one, I don't know. Yeah, I don't know. Yeah.
I guess it's some kind of random process that move from one to
So here I've not looked at that at all, but in the examples, yes. So you could expect. So you can yes. If you add by hand some stochastic process, typically you get this kind of fluctuations. But then the problem is that the properties of the fluctuations depend on the properties that you put in the noise, which you have chosen yourself. In realistic systems, I guess the transitions are mostly rather due to interesting fluctuations, so chaos or whatever. So what I can say for sure is that in this system, there are no spontaneous transition between even when we are in the bistability regime, there are no spontaneous transition between the non-superrotating and superrotating state up to, I think I made simulations up to some very long time, I don't know, 100,000 years or something like that. It's low resolution, so you can run for a long time, which probably is because the system does not fluctuate enough. So maybe if you go to higher resolution, you could observe this kind of spontaneous transitions. In numerics, typically people do what you say, they just add some randomness.
So there is no way to know whether in 1 month.
Is there a way to know? So then it's a different problem. It's a prediction problem. If you know the initial condition now, you would want to compute the probability of transition conditioned on the initial state. Or if you want, you could compute the return time. So yeah, that's what you would want to do, is to be able to know the return time when you have a bistable system like this. So I think this has been done in many systems with maybe idealized systems, some of which I've shown in my introductory slide. For instance, for the multiple jets, there are lots of technical difficulties associated to that. Usually, you need very long times because these transitions are rare, unless you have some unrealistically large noise. So there are some techniques to do this kind of things, some of which we are working on in Lyon. Yeah, but in general, you have to go through this kind of things. It's difficult to have some general law. You have general laws like Arrhenius laws or things like that. It turns out that in the jets in the barotropic vorticity equation, it indeed satisfies an Arrhenius law, but it's not evident at all. And there are a number of examples. Maybe I'm quite sure that some people in this room have worked on examples of transitions in turbulent flows which do not satisfy Arrhenius laws. So there is no universal, as far as I know, there is no universal way to compute this return time.
Bye.
So which plot are you referring to? So I understand the general point, but this?
No, the very first part.
This one? Yes. Okay. Ah, okay. Nobody knows.
Why wouldn't the excitability be fluctuate?
No, absolutely. It could also be purely deterministic. It could also be because there is some forcing at a given moment in time, and then it's. So you're right that you could imagine plenty of dynamical mechanisms to generate this kind of behaviors. Relaxation oscillator, for instance, is a good example. So which is I think close to what you have in mind. Yeah, and it may be the most relevant one. People have done a number of works on that. For instance, there are some simulations with a full model which simulate relaxation oscillation, which have some characteristics like this. So it's probably a good hypothesis, but it's been a debate for a long time in this community, and I don't think it's settled yet. Yes. And that I don't know. It's a good point. I have not found it, but it might exist.
So in the second part of your talk, I lost track of whether you were presenting that as an example of biostability, control parameters, the magnitude, you're applying an artificial force to the top. And that's how you're under control. Were you presenting that as an example of a sudden transition, or was that more a continuous transition? You increase the energy of the force, you simply go to a sequence, continuous sequence.
So
it's three things.
This one? Ah, the most case. Okay. Ah, this. Yeah. So this these are so it's here. I'm just showing 3 different values of the forcing, and I didn't try to check whether it was there was hysteresis or anything.
So we're not. So this could simply be a continuous.
Yes, it could. The thing is, it is indeed relatively abrupt in the sense that it's only well, the system looks like this until we get very close to f naught equals 2. Then it looks like this for a short while, and then as soon as the f naught increases a bit more, we go into something which looks like this and doesn't vary much as we increase f naught. So it's not linear, but it doesn't mean that it's but there is a bifurcation that I don't know. We have.
So if you did this experiment in the dry model, you get. So is the kind of change in the humidity very important to go inside the rubber change the pressure change in nature.
So yes, so if we do this in the dry model, I would expect that you can have if you have no if the setup is purely axis symmetric and you have no non-zonal heating at all, I would expect that you cannot have the bifurcation that I talked about earlier, unless you're counting on the other feedback mechanism, the Hadley cell feedback. So this I did in an axis symmetric model. Indeed, you have a small range of bistability in that case. But otherwise, I think just imposing some eddy momentum fluxes, I don't see how you would excite a positive feedback mechanism if you do that. Your eddy momentum fluxes have to depend on the background flow. Here they don't by design. So I think we are kind of shutting down this possibility from the way the experiments are designed. I didn't do it, but that's what I would expect. Right.
Are you around for a week next week?
Yeah, I'll be around the end of next week.
Yeah, I'm going to talk about it.
Okay.
I'm interested. Most Peter Haynes, I think.
Yeah.
Yeah.
Okay. Well,
Thanks. Yeah.
I'd be happy to. Part of responsibility in that also. I don't know, maybe it's just my voice.
No, I mean, I think the reading has its good spots and bad spots, and of course, it's worse for some people than others. Maybe I have some slides.
Sure.
Well, that'll be that.
That'd be good.
It will appear.
So the talk was recorded, right?
Yeah.
Or
It
just
should all be that.
There'll be a recording, won't there?
Yeah.
So can always
I will
listen.
just, I can appear.
I could hear it just was a struggle, you know.
I don't know, maybe. But it's very close.
Yeah, it's a proxy for temperature.
Yeah.
But that's where the hypothesis comes in.
Yeah.
So one hypothesis is that it's mainly driven by changes in the meridional circulation in the ocean, the thermohaline circulation anymore. I don't know how familiar you are with that, but deep ocean circulation. Basically, you have convection in the North Atlantic.
Right.
Okay, and the water goes back across the Atlantic Ocean, bottom of the ocean, basically. And this circulation is believed to have multiple modes of operation. If you go from a strong mode to a weaker mode, then you bring less heat from the South and North Atlantic, and that could correspond to, in that case, it would be a cooling. It's a topic which makes headlines quite often. So even, again, recently, a couple of weeks ago, there was a paper by some colleagues in the Netherlands which appeared in The Guardian. But was framed as a possibility for the climate of the future, but in a glacial climate, it could have also something like that, where the circulation oscillates between modes where it's more or less intense and brings in more or less heat toward North Atlantic. But there are also other hypotheses which are related to the vertical structure of the ocean in the polar sea. So if you form a halopline, for instance, you can affect strongly the formation of sea ice. The quantity of sea ice has a direct effect on the temperature because it has some feedback. So there are competing hypotheses. There is no consensus. It's already a known problem in the sense that it's several decades that people have been working on that, but it's also a very difficult problem because there are very little data. So, which at the same time makes it very interesting because it means people can be creative.
Yeah, yeah.